Assalamu alaikum everyone, I Hina welcome you all to the online course of electrical measurements. As we have completed the major portion of this chapter, so now we are left only with one topic. Today we will be studying about the various methods of damping. As we have already read about the damping, what is the function of damping in any electrical instrument, we all know that damping is used to avoid the oscillations. So first of all, we will understand what are the different types of oscillations that may occur in an instrument. After that, we will understand how can we overcome those oscillations. Now, oscillations can be categorized into three categories, that is underdamping, critical damping and overdamping. This is also explained using the graph. So whatever damping we will provide to the system, it should be of such magnitude that the pointer comes quickly to its final steady state position without overshooting. That is the reason why we do damping in any system. So damping device should be such that it produces a damping torque only while the moving system is in motion, not when the system will be in rest. So for its effectiveness, the damping torque should always be proportional to the velocity of the moving system. So the various methods by which we can provide damping in any system are: first, air friction damping; second, fluid friction damping; eddy current damping; and electromagnetic damping. Friction damping. Now, we all know that in order to damp the oscillations, we just have to provide a frictional medium such that the oscillations will damp. So here, in air friction damping, the frictional medium that we will use to damp the oscillation is air, hence the name air friction damping. Now, we all know that in any electromechanical indicating instrument, we use a pointer to take the readings, and this pointer is attached to the spindle. So what happens in air friction damping is that this spindle has a vane which is free to move in an air chamber, and by its movement in the air chamber, it's able to damp the oscillation. Coming to the first type, as you can see in the figure that a light aluminium piston is attached to the moving system, and the piston is free to move in the air chamber. Now we will see this, how the movement of piston is able to damp the oscillations. Okay, now we all know piston can either move inwards or it can move outwards. Taking the first case, if we consider what happens when the piston moves in. When the piston moves inwards, what happens to the air inside the chamber? Obviously, the air inside the chamber will be compressed. So the pressure inside the air chamber will increase and it will try to oppose the motion of the piston, and hence the whole moving system. Okay. Now, what happens when the piston moves out? When the piston moves out, so the pressure will decrease in the air chamber. So the pressure on the open side of the piston will be greater than the other side. Again, there will be opposition of motion. So by this opposition of motion, it's able to damp the oscillations. Now this figure shows another way by which air friction damping can be provided. As you can see in this figure, the vane is free to move in a sector of air chamber. The principle is same, that there will be difference in pressure and there will be opposition and it will be able to damp the oscillations. The only difference is that here the vane is able to move in a sector of air. Now coming to the fluid friction damping. This fluid friction damping is similar to air friction damping. The only difference here is, instead of oil, we are using some sort of fluid as the frictional medium, and the fluid that we use here is oil. And we all know that the viscosity of oil is greater than that of the air, so it can provide more friction as compared to air. Hence, the damping force provided using oil will be greater than that provided by the air. This is fluid friction damping. What happens in fluid friction damping is that the discs or light vanes that we also used in the air friction damping, they are also used here. These discs or light vanes are attached to the spindle of the moving system and it's used to provide the required damping. What happens actually is, as the pointer moves, the friction between the oil and the vanes opposes the motion of the pointer and hence the necessary damping is provided. Here one point that can be noted, we can use a number of vanes instead of a single vane. That means a number of vanes can be attached to a spindle in this case. The oil used should follow some characteristics, like it should be a good insulator, it should be non-evaporating, and it should be non-corrosive upon the discs or vane that are made of metal, and its viscosity should not change with temperature. Okay, this fluid friction damping has only one disadvantage, and that is it's not suitable for portable instruments because of the oil that's contained in the instrument. Now coming to another type of damping, that is eddy current damping. First of all, we should all know what we mean by the eddy currents. Now, whenever a conductor moves in a magnetic field, an EMF will be induced in that conductor, and we all know that if we will provide a closed path, then current will flow through that conductor. This current that flows through that conductor is known as the eddy current. Okay. Now, we all know that deflecting torque is always proportional to the current. Here, if we talk about eddy currents, so these eddy currents will also be able to provide some sort of torque. That means these eddy currents interact with the magnetic field to produce an electromagnetic torque, which will oppose the motion, as we already read in the Lenz's law that it opposes the cause. So it will oppose the motion. So the torque produced will be directly proportional to the current, and we all know that the eddy current is directly proportional to the EMF developed, and that EMF is directly proportional to the velocity of the conductor. So we can say that if magnetic field is kept constant, then the torque produced will be directly proportional to the current, and the torque produced will be directly proportional to the velocity of the conductor. Now let's see how eddy current damping works. As you can see in the figure, what we have done, we have just placed an aluminium disc and we have fixed it with the spindle, and this aluminium disc can move in the permanent magnet, so eddy currents will be produced in the disc. These eddy currents will try to oppose the motion using the Lenz's law. That is what we actually wanted. We wanted to oppose the motion. So these eddy currents will exert a force which acts in opposite direction to the motion of the disc, and hence the essential damping torque will be provided in the meter. So we can say that this eddy current damping can be provided in the instruments in which permanent magnet is used, and this eddy current damping is a very effective method of damping. And eddy current damping can be provided using two ways. First, as we used in this case, that we used an aluminium disc. Another way of providing the eddy current damping is that we can place a metal former which carries the working coil of the instrument. Now coming to the final method of damping, that is electromagnetic damping. This electromagnetic damping uses the same concept as was used in the eddy current damping, that the movement of coil in the magnetic field will produce current in the coil. Then that current will produce some torque, and that torque will be used to provide the necessary damping. Here, the damping provided is directly proportional to the magnitude of current, and we all know that current is directly proportional to the resistance of the circuit to which the instrument is connected. Hence, we can say that electromagnetic damping is directly proportional to the resistance of the circuit to which the instrument is connected. This electromagnetic damping is used in galvanometers. So we have all become aware of the different types of damping, that is air friction damping, how it works, fluid friction damping, eddy current damping, and electromagnetic damping. With this we complete our unit 2, and that was all for today. Thank you. Stay connected.